I know, the voice of God telling us the meeting's being recorded, but focus on me today, I guess. So it won't have any of your faces popping up in there, which is good news. So we're going to talk about a couple of different things. You're going to need a calculator and you're going to need your equation sheet. So if you don't have those handy, could you get them handy? I would really, really encourage you to use the calculator that you are likely to use on your next test. I want to show you a thing or two about it. And for the most part, that's a TI for almost all of you, because a lot of you have those TIs. And so I'll be speaking to the TI a little bit, but there's some mistakes that tend to get made, and we want to kind of find and kind of nip those in the bud like right away. So if you guys have those things around you, you also might want a highlighter. I'm going to encourage you to do something today that I've not really done before. It's not a big deal, but it might be helpful for you guys if you have one of those. So I'll give you a second. I'm going to suck on a cup of coffee. There we go. So the first thing I want to do is I want to kind of pick up where we left off. If you remember, I remember where we left off on Friday. You might not, but I kind of remember where we left off on Friday. We were talking about the idea of a space station and false gravity. Do you guys remember that? So, and although I don't really want to talk a lot about that particular idea, because although it's neat, it's interesting, it's just an exercise in shoving numbers together, and that's not particularly interesting for me or you. I do want to remind you about a couple of critical things about it, because it's going to come up here in a few minutes. First, the idea here is that the space station is spinning. It doesn't have to be a donut. I drew it like a donut because it makes the most sense to me, but it doesn't have to be a donut. And we are kind of walking on the outside edge like that. And you're experiencing not gravity. You're experiencing a normal force that is simulating gravity. The reason why you have this experience is because your body has inertia and wants to continue traveling in this straight line. But you encounter the wall applies a force on you this way, and that normal force is what's going to simulate gravity. Now, if you're asked to figure out how fast a space station would need to spin, or a question that's in that range, like how fast is it spinning, how big would it have to be, anything like that, remember that you want your net force to equal MAC. And if you're trying to simulate gravity, then this force, this normal force that is causing your centripetal acceleration, this normal force would have to be equal to mg if we wanted to simulate gravity. It wouldn't be mg, but we would want it to be the same size as mg. And if you do that real quick, you recognize that you can kind of figure out how these things would have to be related. Meaning, it wouldn't matter how big the person was. If we wanted them to have a simulated gravity experience, then we would need to make our space station structured in such a way that this ratio was preserved. So we want the radius to be a certain size, we want the velocity to be a certain size, and then you could experience the acceleration of gravity. Something to keep in mind is we do this kind of thing all the time. A lot of rides, like carnivals and stuff, they manipulate the normal force by spinning you. So if you've ever ridden any carnival ride, like the zipper, have you ridden the zipper? The zipper is one of those things that has and it's probably called different things in different places, but it's got two crossbars. This is looking down on it. And then there's each one of these has and then there's a car on the end of all of these. So this is spinning, and then the whole thing is spinning. You seen one of those? Yeah, I mean, if that's not manipulating, your spinning and your normal force, then nothing is. Ferris wheels do the same thing. They want to make you feel like you're coming out of your seat at the very top. Ferris wheels can spin in either direction. If they spin one way, it feels like you're being thrown out of your seat. And if it spins the other way, it feels like you're being spilled out of your seat. It just depends on which way the Ferris wheel is spinning. So if this is a Ferris wheel and you're in one of these little chairs that's hanging on the Ferris wheel, you're going to be going over the top. And we're using this rotational speed to manipulate the normal force acting on you. the very top, when your basket gets right here, your weight's down, normal force up. We're going to have the normal force get reduced so that the unbalanced force is always towards the center. So you feel like you're being thrown out of the Ferris wheel. They tend to run Ferris wheels in either direction. They don't have to run them one way. They can run them this way if they want. Then you feel like you're getting dumped out of your seat. It's kind of why it rotates. So, no matter which one of these kinds of rides you ride, they're always trying to manipulate the experience you have by manipulating the normal force. Anybody ridden, which was called, it's that space ride at Epcot, when you're supposed to be like on a simulated rocket, Mission Space. That's it. It's famous for having killed people. I mean, that's what Mission Space is famous for. For a while, it was like one person a month. You get all these people going to Epcot in the middle of the summertime. They're from up north. They don't know to stay hydrated. They get into that ride and it starts spinning them up, and their bodies just don't handle it particularly well. Well, they've had to stop spinning the ride now because of that. So there's a green side and a red side. The green side is for people who can't take that pressure. The red side is for people who think they can. The thing to know is they just spin you. That's all it is. The ride spins you to give you a simulated normal force. In this case, it's to make you either feel weightless or to make you feel like you have a lot of weight, as if you're being launched by a rocket. So this idea that we're going to manipulate the normal force by spinning you isn't new. It's how we do a lot of rides. It's how we do a lot of carnival tricks. It's even how we train astronauts. So today, what I'd like to do is I want to kind of talk to you a little bit about some of the ways in which we can talk about spinning. And I'm going to use this as an example first. Anybody ever, if you've gone to the mall, Citrus Park Mall, they've got a huge carousel in there, right? Little horsies and giraffes and stuff you can ride on. The thing about it is we don't tend to talk about how fast people are going on these rides. We tend to talk about how fast the ride is spinning. And if you remember when we first started talking about centripetal motion, I started by talking about this rotational speed versus linear speed. And today we're going to really kind of play that off and talk a little bit more about it. The thing about looking at the difference between linear speed and rotational speed is having to know this concept that the entire ride has one rotational speed. And I'm going to use a lowercase w for this. It's not really a W. It's supposed to be lowercase omega. But no matter how I write it, it looks like a W, but it's supposed to have a W with like some flair. So I know I'm writing it all around my head, but there. It's like a W with flair. That little whoop at the end is supposed to be the flair. It's supposed to make it Greek. Who knows? The way things are going, we might have a hurricane named this in a couple of days. There's going to be a new one forming down there in the old Caribbean. So eventually we'll make it to omega, and that way we'll have gone through all of the Greek letters. I don't even know what happens after that. I mean, we're on theta right now. If we run out of Greek letters, what do they do next? They do like another alphabet? Do they pick a different alphabet to make it different? I don't have an answer. If you have a hurricane that occurs outside of hurricane season, they don't call it a hurricane. And insurance companies won't necessarily cover it because it was a hurricane season. Weird, huh? Yeah. Not that you care. I'm just, throwing stuff out there because, we're all at home now. So anyways, omega stands for angular velocity. And when we deal with angular velocity, just a reminder, it's going to be in things like rotations per minute or rotations per second or radians per second. And I kind of got an expectation that you're going to be able to do conversions here. So when we talk about objects that are themselves spinning, and I might want to figure out what believe it or not, the district just tried to call me. They are the ones who told me I had to be at work today, and they're calling me in the middle of the day. Rude, very rude. If I have, say, 2 kids and I put them both on this ride, I hope all of you realize that the kids both have the same angular speed, but they're going to have different linear speeds. And the reason they're going to have different linear speeds is the kid that's on the outside, he's going around a much bigger circle than the kid that's on the inside. The kid that's on the inside is in a much smaller circle, but they complete that circle in the same amount of time. Now, that's what we demonstrated in class the other day. Today, we need to maybe put some numbers to this. So I want you to imagine that you're a parent and you're standing right here and you're watching these kids go around in a circle. So your kids pass you, and in your head, you count how many seconds it takes for them to come back. And you count to 4. And it says they go around once every 4 seconds. Well, if you're not paying attention, you don't realize I just gave you the rotational speed. Do you realize that's what's been given to you? Because what I told you was they're making 1 rotation every 4 seconds. That's rotational speed. So it's important to understand that when you're doing your homework, you might be given rotational speeds and not even know it. So if they say it takes it makes 2 rotations every 5 minutes, they're giving you a rotational speed. Or they go around once every 4 seconds, they're giving you a rotational speed. They're not going to necessarily say it's doing 60 RPMs. They can hide it, and they're going to try to, because they want to make it a little bit real world. And they also want to let you know this is something that you could figure out on your own. You could sit there next to the carousel and figure out its rotational speed. All it takes is, a second hand of a watch. So what I'd like you to do first is I want you to convert this into radians per second. If you don't remember, I said that we would have to do this. And some of you said that you might need some help with this. We're about to find out who needs help with this. So I want you to convert this into radians per second. If you can't get the answer, that'll tell me who needs help and who doesn't. So take a minute, and I want it in radians per second.
Did you teach us how to do this or no? Because I've been absent.
Nope. I have not taught anybody how to do this. I'm just looking to see who can and who can't. And sometimes it's easier to figure that out by making you try. So when you think you have the answer, just pop it in the chat, and I'll fire back whether you're right or wrong. Oh, please don't give me in terms of pi. I want a number. Yeah, I want a number. There's a reason why I want a number. So there's a couple numbers popping up in there, and I'm replying to people whether they're right or wrong. I might not get everybody because they're coming in fast now. So, Tanner, really? That's a lot of numbers. All right, so I think we've got it down there. That it's 1.57. Now, if you don't know how to do this, that's okay. I'm just trying to get a brief idea of who can do this. I'm going to show you how to do this in just a minute. But before I do, what if I told you that something was spinning at 60 radians per second, and I wanted rotations per minute? Could you please tell me how many rotations per minute this is? I'm trying to identify a specific problem. So the phone call I just got was my principal telling us that we're not allowed to be on school campus. The building is closed. The only reason we would have gotten that is because somebody must have tried to get on the school campus. You can't be on the campus. It's a shelter. So shelter management is there. When I was there yesterday, they were dropping off all the shelter supplies. I don't know that anybody went to the shelter, but they were dropping off shelter supplies. All right, I'm expecting you guys to be about done here, and I'm looking for a specific problem, and I can identify people who make this problem. And here, to see if you guys are making this problem, I'm going to do one more thing, and this is for everybody who said, basically, I don't know how to do this, so I'm not going to try. This is something I need you to try. I need you to do 10 divided by 2 pi. So this is for everybody who doesn't know how to do the conversion at all. Please just do 10 divided by 2 pi. When you've done 10 divided by 2 pi and it's sitting in your calculator, I want you to cover your calculator so no one else can see it. Oh, wait, no one can see it. You're in your home. But thank you for trying. Well, unless, of course, you're in your home and there's people around you. But that doesn't seem to be the case. All right, so everybody tried it? Now, before you look at your calculator again, 2 pi is 6. 10 divided by 2 pi should be a number that's a little less than 2. Look in your calculator and see if you see a number that's a little less than 2. Now, it's possible that you don't see a number that's a little less than 2, that you see a number that's greater than 10. If that's you, you don't know how to use your calculator. And I don't know who you are, clearly, but you probably typed 10 divided by 2 pi into your calculator. And your calculator did 10 divided by 2, which is 5, and then multiplied by pi, which is 3, gave you a number that's like 15. So if you're making that mistake, imagine the kind of mistakes you're going to make on the next test when there's lots of like conversions like this. You need to make sure that if you do 10 divided by 2 pi, that the 2 pi is actually both in the denominator of the fraction. Do not trust your calculator to be as smart as you. But if you tell your calculator to do things, it will do them the way it thinks it should be done. So let's make sure we're doing that correct. And now that that's done, let's talk about how you do one of these conversions. I'm going to do each one of them real fast. And this is for the people who don't know how to do it. And there's not many of you, but there are a few. So let's start with the radians per second. We're going to take that to rotations per minute. I use unit multipliers. Not a big fan of them, but I was never good at conversions when I was in school, and I never got them wrong when I used unit multipliers. So that's what I want you to do. So if you're not good at this, using unit multipliers takes a little bit of time and takes some paper, but you should never get things wrong. The first thing you have to realize when using unit multipliers is that each multiplier is a conversion. So for example, I want to convert the radians into rotations. So in order to cancel out the radians, I have to put radians on the opposite side of where it is now. And then I have to put on the side that's blank, perhaps what I want to go to. Sometimes you can do that in one step. Sometimes it'll take multiple steps. But in this case, I'm just going to rotations. I can do that in one step because I know the rotation. I know the fact that will convert rotations to radians. Next, you need to know your fact that, for one rotation, there are 2 pi radians. Now, this gets rid of the radians and leaves me in rotations, but my answer will be in rotations per second. And I wanted rotations per minute. So I'm going to need another conversion fact. So for my next conversion fact, I'm going to leave the rotations intact, but I need to get rid of seconds. So I'm put on the opposite side of the line. And time is one where you might have to dance it through something, but I think most people know the conversion from seconds to minutes. So not a hard one. Again, I need my fact, which is that for every 1 minute, there's 60 seconds. Now, again, I encourage you to write things out because if you write things out, you tend to make fewer mistakes. And also, some of you, it would not be a bad idea for you to go a step further and multiply the stuff on top and multiply stuff on bottom and then do your division rather than trying to stuff it all in your calculator. Some of you are just not great at stuffing it all in your calculator. So for this one over here, 0.25 rotations per second. This was an easy conversion. You only had to convert the rotation part. Put rotations in the bottom, radians in the top, put my fact, and then, well, it was 0.25 times 2 pi. That left me with rotations per second. seldom am I going to want your answer in terms of pi. Just go ahead and get a decimal. And keep in your head, pi is about 3. I always think it's a good idea for you guys to maybe throw down what it would be if you had 3 for pi and estimate in your head. This is 6 times 0.25, or 6 divided by 4, which is 3 halves. I'm anticipating a number around 1.5. That way your calculator can't lie to you. Anyways, that's all I want to do when it comes to converting. I hope that you guys now are conversion masters, because I really want to pick up this problem with the horses and help us understand how we can make quick comparisons about the speed of the person on the inside horse versus the speed of the person on the outside of the horse. So just a reminder that both people have to be experiencing a centripetal acceleration. And in class the other day, somebody asked me, does it matter whether I put a big R or a small r here? No, I keep switching between them. I'm being very inconsistent, and I apologize. But that's my fault. And I'll take responsibility for that. All right? But I want you to think, if I want to do this, I have to convert from my angular speed, which we said was 0.25 rotations per second, to a linear speed. And I'm going to assume that most of you don't know how to do that, but it's not hard. The conversion's super simple. And it's basically something you probably already know. So if you know this, then you know how to do the conversion. How many of you recognize what I just wrote down? Okay, about 4 of you. That's not as many as I thought, because I figured circumference was something you did like in elementary school. So this is the equation for circumference. Circumference is a linear value, and 2 pi is an angular value. So it is the conversion. If you want to convert any angular value to a linear value, you have to multiply by the radius. That's all there is. So if I want the linear speed, the tangential speed, I need to take the angular speed and multiply by the radius. That's how you convert from a linear speed to an angular speed, or from an angular speed to a linear speed. Right there. But this is a warning. That 2 pi is the angular measure for going around one circle, and it's in radians, which means you can only use this when your angular speed is in radians. Please put that in your notes. That although this is the conversion from angular speed to linear speed, it only works when you're in radians. If you're in anything else, it's not going to work. Which is why the first thing we did was convert 0.25 rotations per second into 1.57 radians per second. All right. I'm going to trick you on the next test. Don't let that be the one that you get tricked by, because if it is, I might have to bring it up in class. But I also want you to think about this. We might not have to actually convert. Not the way you think. You might not have to find the linear speed. There's no reason why we couldn't do substitution and have more than one way of calculating centripetal acceleration. You can calculate centripetal acceleration using the angular speed and not find the linear speed at all. Parent alert. Somebody's parents in frame. Oh, they're gone. I saw it. Did you guys see it? I totally saw it. It was Anthony's parent, just like right behind him, real fast. Yeah. I'm not sure he even knew. He's wearing those headphones. So I think the person was like, stealth. They're back. They're back again. My word. Total invasion of his privacy in the middle of class like this. Unbelievable. Unbelievable. So there you go. The reason I want to point this out is think about this for a minute. Both people on the ride have the same angular speed. They have to. They're both on the same ride. But the person that's further away has got to have more acceleration in order to travel in that circle. It's not obvious that that's true here, but it's very obvious here. That also means that if that person is twice as far away than this person, then the force that they have to use to hold on to the ride has to be twice as big, because it's proportional to how far away they are. Both people have the same angular speed, but the person on the outside has to hold on much tighter. That's why whenever you've seen any of these carousels, the first thing they say is put the little kids on the inside horse, and then the big kids can be on the outside horse, because they're afraid the little kids can't hold on that well. And they clearly, you put them twice as far away from the center, they have to hold on with twice as much force. So that's what that's all about. And I want to make sure you have this. Now look, do me a favor, on your equation sheet. You have your equation sheet out in front of you? A lot of the things we just talked about are on your equation sheet. What I want you to start doing is, that equation sheet is daunting. If you haven't recognized, there's a lot of stuff on there, stuff that we may never talk about. They do that on purpose. They put things on there that you may not ever use or may not ever need, to make it more confusing, to see if you really know what's going on. Now, you cannot add anything to your equation sheet. You can't write any extra equations on it, but I will let you highlight things. So take a second, find the stuff about centripetal acceleration and highlight it. While you're doing that, I'm going to set up what we're going to talk about next. Okay, I'm ready. Are you ready? Good. There was no talking. No one said a word. So I have to assume you're ready. I want you to imagine that you're standing on the equator of the Earth. That shouldn't be hard to imagine. We're pretty close to the equator here in Florida. So imagine you're standing on the equator of the Earth. I would like you to tell me how fast you're going. I've given you all the information you need to do this, except for maybe one thing. But while you're setting up the problem and writing it into your notes so that you can get started with it, I want to know your tangential speed when you're standing on the edge of the Earth. You're going to be surprised, I think. You're going to need a piece of information. And it's not the angular velocity, because you already know that. What's the angular velocity of the Earth? Somebody say it. Really, not one of you? Not one of you knows how long it takes the Earth to go around once? Thank you. I saw somebody mouthed it, and that's a good start. So, Claudia, thank you. I was not happy to see that. It takes 1 day to go around once. So the angular speed of the Earth is 1 rotation per 1 day. That's the angular speed of the Earth. That really doesn't tell you very much, because you're going to need that in radians per second. But you're also going to need something else, and that's going to be the radius of the Earth. And although I'm sure a bunch of you know this, because you just keep this tucked away right in your head sometimes, for those of you who don't, it's 6.37 times 10 to the 6th meters. That is the radius of the Earth. So take a minute. I want you to tell me how fast a person on the equator is traveling. And because, I'm very interested to see that you know how to use your calculator, I'm testing something else right now, and that is your ability to use big numbers. So when you have the answer to this, if you could put it in the chat, I will tell you whether you're right or wrong. And I will be impressed a little bit. And while you're doing that, I'm going to do like what everybody else does and check my hair, make sure it's good. Yeah, that's good stuff right there. The camera's still too close. It's really giving me that triple chin thing. I need to up my camera game a little bit, elevate it, give me that top down look. Better highlighting too, accentuate my eyes better. I'm just going to keep talking, because I figure this is going to go on YouTube, and some chucklehead's going to find it long after I'm gone and say, who the heck was this? And why are their physics videos so terrible? And we'll know why. We'll know why. Not one person has put it in there yet. Come on, this is my smart class. Like, there's some smart people here. A few of them. Many of them. And Tanner, you give me 8 different decimal places, and I'm going to smack you in the brain. You put your head in the fan. And you know I have a fan. All right. It's 10:01. We still have a few more things to do. Not one person. Look, you're going to make me read my text messages or something. This is taking too long. All right, so as numbers pour in, I will be telling you whether you're right or wrong. But I'm not going to tell everybody. I'm just going to tell the person. So far, 3 different people, 3 different numbers. All right, good stuff. One of them might be right. Who knows? Really, nobody else? It's always nice to have at least one of these numbers confirmed. You know, when you start seeing a repeat number. Of course, there's I've answered everybody who's put something up there so far. Thirty more seconds. Oof. 15 more seconds. I'm getting sad. I am. Carolina, you can believe me. I can be sad. It's okay. Samantha doesn't think I'm sad, but I am. I'm sad. Only 4 people were able to do. Oh, Carolina popped a number up. Bummer, dude. And Anaya. Okay, so 3 people actually had the right answer. It is 463 meters per second. Now, if you were unable to get the answer, I'll give you a little bit of sadness. Here's my sad face. I know it's a little sad face, but that's because I made my face all little on the bottom there. But part of the reason probably you're not getting the right answer is probably a conversion issue. But you will need to put everything in radians and seconds if you want your answer to be in meters per second. So we can't leave it in 1 rotation per day for sure. But more importantly, I wanted to also make sure that you guys had access or knew how to deal with the fact that this is a big number, because we're going to deal with some really big numbers in a minute. And sometimes you guys know how to use your calculator for this, and sometimes you don't. So let's talk about what was necessary here, because I was hoping to get more of you with that. And I want to talk about this speed. I mean, this is not small. This is 463 meters per second. I don't think you guys have any context for whether that's fast or slow. It seems fast. It's a big number, but how fast is it actually? And is it real? I think that'd be nice to know. So let's handle all the folks who couldn't do this correctly, starting with a conversion. 1 rotation for every 1 day has to be converted to radians per second. So let's start there first. There's a lot that has to be done here to convert. I think rotations is easiest to handle first because we need radians. So that's going to be for every 1 rotation, 2 pi radians. That one's pretty straightforward. But it's that time one that's going to be kind of a pain, because I don't think I can just do 1 conversion to go from day to seconds. I don't have that in my head. I do know that I'm going to put day on top, and I'm going to put, let's go hours on the bottom. So for every 1 day, there's 24 hours. And then that's still not good enough. I need another conversion fact. So I can go hours to seconds. You might need to dance it through minutes, but I know that for every 1 hour, there's 3,600 seconds. And I'm doing that mostly because I ran out of space. If I had more space, I would have put minutes and then seconds. But I ran out of space. So the first thing you had to do was convert this into the angular speed correctly, which is going to be 2 pi on the top and 24 times 3,600 on the bottom. That's the angular speed. And this would be in radians per second. Now, I don't really know what that is, but whatever that is, I have to then take that and multiply by the radius of the Earth. So that's going to be that 2 pi on the top, 24 times 3,600 on the denominator, and then you have to multiply by 6.37 times 10 to the 6th. And here's where I have some concerns too about your calculator skills. And the reason why I wanted you to use the calculator you're going to use on your test and not your phone calculator is I want you to make sure that you're using the right button to put that in. And look for that button. That's the button you need to find. If you don't know how to use scientific notation on your calculator, you need to learn. So, oh, I saw that. Mariana, what'd she bring you? Was it coffee? A kitty? She brought you a kitty? That's a thing? Like you can just get an emotional kitty whenever you need it in the middle of physics? I bet a lot of people could use that. Right in the middle of physics, somebody brings you a puppy or a kitty. It would make it so much nicer every day. Oh, well, you're in mean old physics. 6.37, then hit the EE button, and then 6. Do that. That's how you put it into your calculator. And I hate to break it down to like actually little buttons, but you need it sometimes. Do not ever use 10 to the X. Don't ever use it. It will screw you up a lot. This is a function. This is the anti-log. This is not a function. It just stores the number correctly. So when you type it in, it'll look like this in the calculator, 6.37 E6. That's how you should put it into the calculator. If you do it that way, you're bound to get the right answer more frequently. So please do that. But now that that's done, I want to come back to just all of this. Let's get rid of all the calculation, all this garbage. 463 meters per second is how fast you're traveling by just standing on the equator. Now, to put perspective to this, the speed of sound is 333 meters per second. So when you break the sound barrier, you have to go that fast. You are breaking the sound barrier. You're going faster than sound travels when you stand on the equator. Now, you might think, well, luckily I'm not on the equator. We're at latitude 40. So if you want to know how fast we're traveling, all you need to do is multiply by the cosine of 40 degrees, and you have how fast we're traveling here in Florida. And if you do that, and some of you probably are because you're curious, you're finding that we're still traveling pretty darn fast, even though we're on the equator. This is why we launch rockets here, because rockets get that added amount of speed when they take off because they're already traveling that fast. All of us are. You want to talk about hurricanes? We have mountains traveling that fast that stir the air as they spin. This is why the jet stream is so fast. The spinning Earth really does a number on the atmosphere, continually causing it to be stirred and to be mixed up. And you add heat to that and the sun and the moisture. Yeah, hurricanes. Thus today, hurricane day. So it's pretty crazy to think that that's how fast everything's traveling on the equator of the Earth. But also, because this is supposed to be about centripetal motion, don't forget the fact that in order for you to stand on the equator, you must be experiencing an unbalanced force so that you can travel in a circle, which means if gravity is pulling you downwards and the normal force is pushing upwards, when you're on the equator, those forces are not balanced because you're traveling in a circular path. They have to be. Weight has to be greater than the normal force on the equator, which means you feel lighter on the equator than you would at the pole. And this isn't small, this is measurable. And you can calculate how this is different. All you need to do to calculate it is consider that you have an unbalanced force. I make weight positive because it's towards the center. And that has to equal m v squared over r. We just calculated v. You could figure out what this change in normal force is. That's small, but it's measurable. You feel lighter because there's less normal force on you at the equator, so that the forces can be unbalanced. All right, that's a whole lot. That should give you a lot of what you need to do for your homework, but there is one more thing that we do have to talk about. And I know that we only have a few minutes left of class, so I may or may not be able to finish, but we need to take a moment and talk about gravity. Up to this point, gravity for us has been talking about weight. In fact, all we've been saying is that it's mg. But the truth is, that's been a lie is the wrong word. It's been an oversimplification. We've been able to use this because, well, we're on the surface of the Earth and the acceleration of gravity seems to be the same on all of us. Well, today, you need to be able to tell me why the acceleration of gravity is the same for all of us. And that's because I need you to know about the actual force of gravity. Remember when we talked about it, I said that the force of gravity is a force of attraction between all objects with mass. So today, we need to talk about how we actually go about calculating the force of gravity. It's not particularly complicated, which is why I'm treating it almost like a footnote. But if we have two objects, we'll need to know their mass in order to figure out the force of gravity. And we're also going to need to know how far apart they are. The closer things are, the bigger this force gets. And the bigger things are, the bigger this force gets. There are two things that control the size of this force: your separation distance and the size of the objects. The force is like this. It's m1 times m2 divided by the separation distance squared. This is Newton's law of universal gravitation. But that's a lot, so force of gravity will do. However, it's not done yet, because if you look at this, the top of this is in kilograms squared, and the bottom of this is in meters squared, but force is newtons. So there is a constant that converts this from meter squared per kilogram squared into newtons. This is a big G, though. So it's not little g. This is not 9.8. This is called the universal gravitational constant. Find it on your equation sheet, please. First page of the equation sheet has all of the constants that you're allowed to have on the test. So they won't give it to you, and I won't give it to you on your next test either. You need to be able to find it. Look for capital G. When you find it, highlight it. We only use a couple of the constants on that page. It's good to know where it is. Have you found it? So take stock of that number, 6.67 times 10 to the negative 11th. It's very small. And like I said to you guys, gravity is the smallest force, so therefore, this is a small number to scale it correctly. It takes a lot of mass in order to have a reasonable size force. Look at those units too. They're kind of a pain. It's newtons, newtons, meters squared per kilogram squared. It has to cancel out the units that are here and leave you with newtons. That's why it's a weird unit. Now, we don't have much time. So I need you to practice this though. And there's an easy way to practice it. I want you to calculate the force of gravity on you from the Earth. Now, this is also the same as the force of gravity on the Earth from you. It's the same force because it uses both masses. In order to do this, you're going to need something from me. What do you need from me in order to do this?
Mass of the Earth.
Mass of the Earth. That's right, because you already know how far away from the center of the Earth you are because I gave you its radius. So you just need the mass of the Earth, which, you know, it's kind of stupid, but I have all of this stuff tucked away. Earth's a big boy. 5.98 times 10 to the 24th kilograms. That's right. Earth's a big boy. Definitely been maybe hitting the sweets a little too much. But there it is. Now take a minute and see if you can do it. It's a lot of scientific notation. You might need your mass. And to do that, if you want to know what your mass is in kilograms, just take whatever your weight is in pounds and divide by 2.2. That's a quick estimate of yours in kilograms. So I'm going to lie and say that mine's 100 kilograms. So the force of gravity on me would be that big number, 5.98 times 10 to the 24th, times, you know, that 100, because that's me, divided by that 6.37 times 10 to the 6th, all of that squared, times G. Oof. And then you're going to have to get a number. So we're going to take a second. We only have 2 minutes left. But how do you know if you have the right answer or not? When you finally mash all that together, you're going to get just some number. I see you all working, which is good. We only have 60 seconds left. And although we should stop and say the pledge, I don't have a flag up here. But I know what I'm having for lunch. So we could get the lunch menu, at least the lunch menu in my house. I think Anthony's going to have lunch too. His mom keeps going in there and doing stuff. I think she's doing the laundry. I got to do my laundry. All right, here. Because our last 30 seconds is clicking away. Here's what you need to do. If you want to know whether you got the right answer or not, it's really easy. Divide by your mass. You're going to get 9.8 if you did it right. We already know how to calculate weight. We've done it before. This should give us the weight you would get if you just multiplied your mass by 9.8. So if you take this huge number and divide by your mass, it should give you 9.8. That's how you know if you've done it right now or not. So we're going to stop here. We are not quite done, but you have more than enough to finish up your homework. I'm going to get that question a lot today, so I'm just going to head it off. Are we going to have a quiz tomorrow? I don't know. We're going to go over some of your homework questions tomorrow. If things are looking good, I say, yeah, let's have that quiz. I mean, if there's going to be a lot of A's. Things aren't looking good. Look, it's a hurricane day. Maybe we'll wait till Monday. But remember, I want to stay on target to finish with no homework for the Thanksgiving break. And I know you want us to as well, right? So let's see how things go tomorrow. Get that homework done so we can talk about it in class tomorrow. Okay, guys? And that's going to be it. I have to turn you loose because I don't know if you can hear it, but the bell's ringing. What's funny is at the school, it probably actually is. They ring the bells. It's on the schedule. So anybody in that shelter, they just got woken up by the bell. So you guys have a good day. This was a lot of fun. And look for that grade. I'm going to give all of you extra credit.